Hello, everybody. My name is Phileas Daisley-Guest. I'm an academic innovation applications developer on the AIS team here at Wolfram. And today I'd like to tell you a little bit about Wolfram Notebooks for GIS coursework. So first of all, what's this talk about? We're going to talk a little bit about managing and representing geographic data in the Wolfram language. And then we're going to talk a little bit about some applications extending Wolfram language GIS functionality through first external services and then through built-in Wolfram language tools. I would like to acknowledge before I get into the actual nitty-gritty that this presentation is the result of a collaboration with Gordon Longsworth, who's the director of the College of the Atlantic GIS Lab. Gordon's insights into GIS education were of great help during the preparation of this talk, so I just want to make sure that if Gordon is watching this, Gordon, thank you very much for your help. So let's get straight into it. In the Wolfram language, there is a large amount of built-in geographic data that you can access through what we call the Wolfram language knowledge base, the Wolfram knowledge base. The Wolfram knowledge base is this large collection of data about the real world, which Wolfram curates and builds into the Wolfram language. You can read more about it on the website in the core areas section. And essentially what it allows you to do is from a Wolfram notebook, directly in Wolfram language, it allows you to bring in data about the real world. Part of Wolfram's goals to make everything computable, basically. One of the ways that we do this is through what we call named entities. So named entities in Wolfram language represent named things that the language knows about, essentially. And these are objects that you can use in functions. They're computable. And in order to discover them, you can use this control equal, or as of this latest version, I believe you can also do equals open square bracket and then type something in. So for instance, France, and if I run this, I'm not going to reevaluate everything. I will get an output, which is the entity for France. So many entities in the Wolfram language represent geographic things. For instance, they can represent countries, they can represent cities, mountains, lakes, the locations of the Apollo landings, or universities. Many geographic classes can represent entities, essentially. Some of these entities are going to be grouped into what we call entity classes. For instance, a chain of mountains like the Andes might be represented in its own class. Countries in the European Union might be one of them. All US counties, etc. If you want to list entities that are part of an entity class, what you can do is you can call entity list around the particular entity class that you'd like, and it will return a list of the entities in that class. Entities can also represent things that are not geographic, for instance, plants or animals or historical events, etc. In order to get information about entities, we can ask for properties of the entity using this square bracket property notation. For instance, if I'm interested in the area of Mount Desert Island, I can simply ask for its area like this, and I get 108 miles squared. If I'd like to get the full list of properties that are available for a particular entity, I can use the properties property, so something like this, for Mount Desert Island again. And it shows me that I could ask for any of these particular properties as an entity, as a property of the Mount Desert Island entity. We can also get all of the information that's available from a particular entity in one go, for instance, as a data set like this. So in this case, I'm saying I would like from Mount Desert Island, from the property, from the entity Mount Desert Island, I'd like a data set in which anything missing has been deleted. And here I've just added, make it so that I can only see up to 6 things from this data set at any given time. So only show me the first 6 rows so that it doesn't take up too much room in the screen. So we can see, for instance, it knows that it's in Hancock County, it knows its total area, its coordinates, what country it's in, and 17 things in total, it seems. I mentioned earlier that entities are computable. And what this means in practice is that you can use entities or data from entities in functions. And Wolfram language will try to interpret the information as sensibly as it can. So For instance, if I want to represent a cutout, a polygon of Mount Desert Island as a satellite satellite image styling, what I can do is I can just say geographics with geostyling satellite of this geopolygon of Mount Desert Island with no background, and it will return this nice cutout of Mount Desert Island. There are many different kinds of geographic entities in the Wolfram language. I really don't have the time in this hour to go through all of them, but just to give you a sense of what there is, you can go to the Geographic Data Wolfram Guide page in the documentation, and you'll see this large list of all sorts of different entities that you can click through and explore and start discovering things that way. So as another part of the Wolfram knowledge base is curated spatial data that you can access through functions. For instance, we have functions like geo-elevation data or geo-wind speed data to access these, to search for curated data that's available in the Wolfram language. These functions are incredibly useful, and they're very convenient and easy to use, and they allow you to essentially, in one line, import a bunch of real-world data about things, all the way from elevation data to Earth impact data and earthquakes, or geomagnetic model data, et cetera, et cetera. This is a really useful feature in the Wolfram language, and really these are really helpful functions. Let's take a look at a couple of them in practice. So one of the common things you might want to do if you're working in a GIS context is you might be studying digital elevation models. So in order to get a digital elevation model in the Wolfram language, it's as simple essentially as just saying, I would like geo-elevation data for this particular place, this particular region, and then I can choose my projection and my unit system. In this case, I've said I want it to be a metric unit system. And I'm reversing it just because there are differences between in the coordinate systems for arrays and for, so this is an additional consideration that I'm making because I know that relief plot expects things to be represented slightly differently. So I make this, I fetch this geo-elevation data and assign it to this MDI DEM digital elevation model variable. And then to make a relief plot of these data, it's basically it's just as simple as relief plot of this variable, and I've added plot legends automatic so that I get this nice little legend here on the side. I could go into more detail if I wanted to change things like the color scheme, or make sure that or add some labeling, etc., etc. I could go into the documentation, see what options are available, and really fine-tune the graphic visualization here. I could also make a contour map, and the same goes. I can change the distance between contours or the number of contours with additional options. This is just a very simple demonstration to show you that with a line of code, you can already get most of the way there in terms of getting a nice visualization of your digital elevation model. So here it's list contour plot of our variable with some additional options for styling. And there's the result. So another function that we have is wind vector data. In this example, I'm going to get some wind vector data covering Maine for yesterday's winds, so now minus exactly 1 day, and I'm going to represent this as a stream plot using geostream plot function, the geostream plot function in the Wolfram language. So the first step is to get a list of equally spaced points covering the region that we care about, in this case, Maine. So I can say I'd like to have a coordinate bounds array for the geobounds for this particular region, and then I'm going to make sure that every point that we get is wrapped with geoposition so that it's represented as a valid geographic position for this next step, which is getting Maine wind vectors. So here what I'm saying essentially is apply this wind vector data function, which is going to fetch wind vector data over every geographic position in this main grid points variable, and then flatten the result. So then if we randomly sample from this result, we can see what an individual geovector would look like. And in fact, you could have typed this in manually and made up your data if you cared to. or you could have imported this from real data and parsed it and formatted it this way. This is just what the textual representation looks like, essentially. So then once we have this main wind vectors variable, we can just plot it as using GeoStreamplot and get a nice streamplot visualization of the wind yesterday around this time. Okay, here's one more example with earthquake information. Earthquake data is, in this case, I'm saying, give me earthquake data for everywhere in the world, magnitudes between 6 and 9 from the 1st of January 2024 to today, and only show me up to 6 things at a time. Make it a data set and assign it to this variable. And here we get the output data set, which shows us we have the period at which so when did this happen? What magnitude was the earthquake? What was its number of phases? What was its position, etc., etc. And if I want to extract some information from this table, for instance, the position value, and plot it on a map, I can just go earthquakes data. I can take this variable that I've set, ask for all of its positions, its values, because I want it to be only the values and not the key value pairs for position and then the value. And then I wrap this in GeoListPlot with a couple additional settings for a couple additional options for styling. And here's the output. We get a nice Winkle triple projection map of the world with the location of the earthquakes that we've retrieved. So aside from the built-in data from the Wolfram knowledge base, we can also just start representing geographic information that either we generate ourselves or we import from some other source without relying on the Wolfram knowledge base. So let's talk a little bit about how we might represent and compute with geospatial data representations. So the first thing we might be interested in is just representing geographic positions. This is what you would use in Wolfram language. You would use geoposition or geogrid position for this. Geoposition lets you represent geodetic positions, essentially latitude longitude pairs. And the way that it works is very straightforward. It's geoposition with a list containing latitude followed by longitude. So in this case, we can use this to define a variable null island, which is latitude and longitude 0, and then we can show where that is on a map, and we see that it's over here in the Atlantic Ocean. Sometimes we might want to use coordinates that are in a different coordinate reference system, and we can use geogrid position for this. So for instance, maybe I have data that are represented in Olber's projection, and I can use geogrid position with the coordinates in Olber's projection with the tag, with the second argument Olber's, to say this is in the Olber's projection, and when geographics sees this, it's going to convert it automatically to the appropriate geoposition so that you can use it inside of geographics commands. If I want to convert it back to a geodetic position, I can simply say geoposition of that particular position, and it will convert it to the latitude and longitude coordinates. I can also represent lines or polygons geographically. So if we want to represent lines and polygons, lines are essentially just lists of points that are with a line drawn in between, and polygons are just lists of points that are drawn as filled shapes. So here's a short demonstration. Let's make a list of cities specified as entities, and then using GeoPath wrapped around our list of cities, we can trace a line on a map using geographics of GeoPath of our list of cities. So in this case, we have a few different options. We could plot the geodesic, or it might be that you want your line to be a straight line on a Mercator map, in which case you could use a run line, or you also have the option of using a great ellipse to trace the line, of using great ellipses to trace the lines between point pairs. In this case, we just used geographic entities directly in the function, and it worked completely fine. You might be tempted to do the same thing to represent a polygon, but the trouble is that there's an ambiguity there. If you ask for the polygon that is made out of a list of cities, are you asking for a polygon that is made by going from one city to the next in sequence? Or are you asking for a polygon that is the composite polygon made out of the shapes of every city? So because that's ambiguous, we don't let you do it by default. And essentially, the solution here is that first you have to retrieve the positions from the cities. So here, using entity value, I'm getting the position from the cities, setting that, assigning that to a new variable. And then if I want to trace a polygon, I can simply go geographics of geopolygon of these city positions, and I can specify what type of line I want to use. I also specify in the second argument here that I want it to be the smaller area. So what does this mean? Well, essentially, the idea is on a sphere, a polygon specified by a list of points can mean two things. It can mean a smaller area, or it can mean the opposite, the complement, the area that spans the rest of the globe, essentially. So here's what it would look like if I say I like the smaller area joining all of these cities, and here's what happens if I say actually I'd like the larger area that is represented by this, that goes through these cities rather. We also have functions built in for representing hemispheres. So for instance, if I want to know what is the geohemisphere around my particular position, or the position that my IP address encodes, I can go hemisphere of here and wrap that in geographics to get a visualization. I can also ask for the geohemisphere boundary around a particular point. And I could ask for what is the hemisphere of the Earth based on a particular time where it's currently day or where it's day. So for instance, for what hemisphere of the Earth, where is it currently day right now? Or I could ask, where is it currently nighttime? Or I could ask for the terminator between daytime and nighttime. And these are all built in, and you can use these. You can then, whenever you compute one of these hemispheres, you can then treat it like regular geometry and do any kind of additional processing that you'd like to. In order to plot functions, to plot geographic data, we have a number of different functions. We've seen a couple. The most general of these functions is going to be geographics. Geographics can be used for almost any kind of geographic plotting. It's a very flexible function. Sometimes there might be functions that get the job done a little bit faster, depending on what exactly you're doing, and we'll see some examples of that a little bit below. But for now, so here's just one example using geographics, where we're making a map of European countries filled out with their country flags. So the way this works is that I set a local variable called countries, which is equal to the entity list of countries in the European Union. And then I get the polygons for each of these countries and the values for each of these countries a flag, and essentially I thread them together with geostyling of geoimage, so that for each country, the country is the flag is represented inside the polygon for the particular country. And so in this case, it takes let's say this doesn't count, so it takes 3 lines to get this visualization. In many cases, you might just have a bunch of different locations and you want to plot them on a map. The easiest way to do this in the Wolfram language is going to be geolistplot. So with the list of cities that we defined earlier, I can just say geolistplot of this list of cities. I've got this little call out, which I've iconized, in which I'm also saying label these cities by their names. And I add a couple different options for styling, and I get this output here. I might also have be in a situation where I have a bunch of values, a bunch of locations that have values associated with them. In that case, I might use something like geo bubble chart or georegion value plot. So here's one example in which I'm getting a bubble chart of the countries in Asia by population. And so again, local variable for regions, which gets an entity list of countries in Asia. And then I get the bubble chart that threads together regions, so the individual countries and the population values for these countries. So we get a list of country to population rule specifications, these key value pairs, basically. And I get this nice visualization as my output, and I can hover over different bits and see for any particular point what the population is. I could go into more detail here and say I'd like the population for a particular year. In this case, I'm just looking over some simple examples to give you a taste of what geographic computation looks like in Wolfram. So here's an alternative. If you have, instead of having particular locations that you want to represent, maybe you have regions that you want to represent with particular values, in which case you'll use something like georegion value plot. So it works very similarly. Essentially, we've got the same kind of behavior, the same kind of structure and syntax we had before, but now we're using the regions that we're plotting are represented as actual polygons and colored by their values. We can also do things like contour plots and heat maps. So earlier I had this example of a digital elevation model. One of the things we could do if we wanted to circumvent if we wanted to use not an array of values, but if we wanted to use actual geographic data with sort of georeferencing for every point, we could do this using geocontour plot. So here I'm saying get some geoelevation data for this Manicouagan Reservoir in Canada. Make sure that each position is represented as a geoposition, that each point is represented as a geoposition, and give it to me in the metric system, assign it to this variable, and represent it using geocontour plot. Again, I'm not showing you I'm not going into very much detail in terms of what options you might have, but you can hover over the contours here and see what heights they correspond to, and you could also go into the options and change the number of contours and the distance between contours, etc., or the coloring and many other settings. You could use the same data also to represent a geographic heat map using geodensity plot. Another thing you might try is you might be interested in representing the density of data in particular locations. So you could do this using histograms. You could do a smooth histogram of the earthquake positions that we computed earlier using geosmooth histogram like this. Or if you wanted to have binned data instead, you could use geohistogram, which by default gives you these hexagonal bins. I've shown you an example already of using GeoStreamPlot. So you've seen some example of the syntax there. I just want to mention that you can use the same syntax to make a GeoVector plot if you don't want to have this nice, interesting stream interpolation. For some applications, it might be distracting from what you're actually trying to say or show. Wolfram Language has amazing graph functionality, and this extends into geographic computation and GIS stuff with the Wolfram Language. So if you are interested in, for instance, representing networks using like on the planet or in some kind of a geographic reference, you can do this. You can do this using geograph plot or geograph value plot. So here's just an example. I've got a variable here which I've assigned a list of city rule, like start to end city pairs where it's capitals in Europe to Rome. So here is a list of city connections to Rome, essentially. And we can use this to illustrate the saying, all roads lead to Rome, in one line, using this geograph plot statement here, where I'm saying geograph plot of these Rome city connections. And I'm going to use a driving graph layout so that the edges are actually driving directions that you might take to get from one point to the next. If I have a weighted graph and I'm interested in representing weighted graph data, this is where I would use geograph value plot. So here's an example. I didn't show earlier the flight data function, but this is another function that we can use in Wolfram Language to get to stream in information about flights coming in and out of particular airports. So I could say I'm interested in flight data from Chicago, or going to Chicago O'Hare. Oh, sorry, from Chicago O'Hare, from the Chicago International Airport, going anywhere, and I'd like the information to be from yesterday, and then I can simply represent this visually using geograph value plot like this. So I can then hover over individual edges and see, how many flights left Chicago to go to these other airports in the United States, in this case, yesterday. And it's, it's just I think it's quite amazing that this is just built in and so easy to use and play with. Okay, we have many other tools for geographic calculations. So one of them is travel directions. If you want to get travel directions between a list of cities, you can represent that using the travel directions function. You can then plot the journey for a particular computed set of travel direction instructions using geopath and inside of a geographics command. And you can even represent the individual steps that are suggested from the travel directions function by getting the dataset property of the travel directions function output. And in this case, I've just added a couple. I've just said, please only show me up to 4 things from this dataset at a particular point. We also have GeoAntipode if you want to show the position that is on the other side of the world from a particular position. For instance, if you wanted to make an MIT world sandwich, so one slice of bread on the MIT campus, where would the other slice of bread have to be in the world to make a world sandwich? It turns out in this case it would be slightly south of Australia, so it would be a wet sandwich. But this is a convenient function for many different kinds of applications where you need to quickly know what's the other side on the world, what's the other the position on the opposite side of the planet. We can also use find geolocation to do what's called forward geocoding, so looking for particular locations by street address. Here's an example where I have the address of the MIT campus, and I say find geolocation of this address, and it will return the position of the MIT campus, and then I can use geolistplot to represent that position on a map. I can also go the other way around using geoidentify. What geoidentify will do is it will find a geographic entity, like a built-in named entity in the Wolfram language that corresponds to a particular position. So for instance, here I might say identify a university at this position, and it understands from the position that I gave it that this is referring to MIT. We also have functions like GeoNearest, which allow you, given a particular entity, to find other entities of a given type that are nearby. So if I want to know what are the 10 universities that are nearest to MIT, MIT is the nearest to MIT, and then here are the 9 following universities that Wolfram knows about, sorted by distance to MIT. I could also use something like random geoposition if I'm interested in sampling random positions in a particular area. So in this case, I'm saying I'd like 100 random positions inside of Arches National Park. And then I'd like to represent that in a geographics using the geopolygon of the Arches National Park as the background, so just to give a better sense of where the points are being sampled from. This is really just a tiny sample of the geographics functionality and the geographic computation and general GIS functionality that's available in Wolfram Language. There are many other things like geodistance, geolength, geoarea, not to mention all of the functions that are being contributed by users on the Wolfram function repository or on the Packlet repository. Okay, so I want to spend the rest of this presentation talking a little bit about some applications and how you can extend Wolfram Language to do more advanced GIS and geographic computations that there isn't necessarily built-in support for yet. So one of the things is that you might be interested in using base maps that aren't available by default in the Wolfram as geo backgrounds in geographic specifications. One way that you can do this is using external geo servers. What we currently have support for is XYZ geo servers, which are geo servers that fetch tiles specified by an X, Y, like a position of the tile is specified by the index of the tile specified by an X and Y parameter, followed by a zoom parameter, which is the Z parameter. So, for instance, if I want to use external base maps using GeoServers, what I might do is here I've just defined an association that contains a list of GeoServers that I know about that are provided by USGS. A GeoServer specification is essentially just a string template. So here it's going to be the URL for the endpoint, with a slot for X, a slot for the zoom, a slot for X, and a slot for Y. And then, so I've assigned this, I've made this into a little association, and now I can, from this association, I can list all of the available servers that I might want to use. And if I want to use a particular server, I can just say, okay, I'd like the value for for instance, if I wanted to use this USGS hydrocached, I could say base maps association USGS, and then USGS hydrocached, and I could use this as the argument, as the option specification to the GeoServer option in a geographics command. So like this, for instance, geographics of France with GeoServer goes to this GeoServer, and it will represent France with this particular GeoServer, this particular base map. You can go look through the internet and find other free and publicly available base maps. There are many different kinds. There are some that are provided by OpenStreetMaps, and these are things that essentially, once you have the endpoint, it's very straightforward to just use it as an argument in Wolfram Language for a geographics statement. So here's just an example in which I'm getting the world base map for each of these layers. Another thing that you might be interested in doing is using Wolfram Language to connect to GIS or other kinds of geocomputation APIs. So here's an example of just a simple case of doing this, where we already have a forward geocoding function in the Wolfram Language, but this is just for demonstration, an example of how you might connect to an external API. So here I'm defining a function called mapbox forward geocoding, which is going to send a request to mapbox given an address string and a limit parameter which sets how many results I'd like. And what it does is it will build a string template that fills in the endpoint template with the appropriate parameters to make a request to the API. So in this case, what it wants is the address string, the limit parameter, and my API token, which I've iconized over here. So what the string template does is it allows me to encode this. It allows me to represent this template, and then using this bracket notation as I might with a function, I can fill out the template with the particular parameters that I want, and then import the resulting URL as raw JSON, represent that as a data set, and then extract and wrangle a little bit of the results so that I can represent them as geopositions. And so if I do this, if I run this, I can then, it outputs the appropriate position for the address. And I could list multiple best candidates based on the address if there are multiple results that are provided by the API. So a slightly more complicated example of this is this function over here, mapbox isochrone. I won't go into the detail of how this is implemented too much because it's essentially just the same thing, but with more parameters. And what this function will do is it will find the polygon showing what is within a particular distance, a particular temporal distance. So for instance, 15 minutes away from the Ray and Maria Starter Center at MIT. And so the way that you would use this is you might say, I'd like a mapbox isochrone from this particular, the result of forward geocoding this address, so a particular position. I'd like the first position that I get out of this. I'd like to know what is within a 15 minutes walk of this address. And then I'd like to represent that geographically. And we get this polygon over here, which again is just geometry that you can export, you can compute with however you like. You might also be interested in accessing remote sensing data. So one thing that one way that you might be able to, one way that you might like to do this is using the remote sensing packlet, which is the packlet that I wrote last year. So you can import this using this statement once you've installed it. If you just look up Phileas Guest backtick remote sensing backtick, or without the backticks, you can look up the same thing. There's a click to copy code snippet on the Packlet documentation website, which will tell you how to install this into your notebook, and then you can just use this needs once when you want to import this, and you can start using it. So here's how it works. The Gibbs data function gives you a list of all of the available remote sensing services that are provided by the NASA Gibbs service. There are over 1,100 of these, and this is just a shortened, shallow list here where you can see that there are a bunch of these plus 1,099 others that are hidden from view here. And so what this function allows you to do is I can say I'd like, okay, Gibbs data of a particular thing. So for instance, if I say Gibbs data of this layer, it will show me information about this layer. And so I know, for instance, that this is a layer that has an option for date specifications, and this is what the default date is, this is what the template object looks like, etc., etc. Behind the way that you would then retrieve imagery is using Gibbs GeoServer of that same name, and this will build the GeoServer template for you, so that you can simply say geographics of a particular area with GeoServer set to a particular Gibbs GeoServer, and it will represent that imagery for you. So for instance, here's an example where I'm fetching NDVI imagery of France over the last 12 months and animating it using list animate. So here's the result of that line of code. And what I like in particular about this is that you can see how the the snow and ice expands and contracts with the fluctuation of the seasons in the mountainous regions of the Alps and the Pyrenees here. Okay, so now, aside from using external services like APIs to extend GIS functionality in the Wolfram language, what we could use is we could also just use built-in tools. Here's an example in which I implement a function for hill shading. So hill shading is a technique in which we assuming the sun is infinitely far away and all of the sun's rays are parallel, and the digital elevation model is a flat plane. So these assumptions fall apart for very large regions, but over a small enough region, these are fairly reasonable. We can represent what some approximation of the shadows that are cast by the sun at a particular time of day based on its relative orientation to the landscape and its altitude angle. Its azimuth and its I forget the exact terminology. So here's the example, right? First, using geoelevation data, we import some elevation data for Crater Lake in the Mercator projection. We can preview this data by representing it as an image like this. And then I'm not going to go too far into the explanation of how this works exactly, but essentially this is just computing the gradient of the image and then doing a little bit of additional sort of some trigonometric operations to simulate the cast shadows, and then representing the result as an image. So there are a few assumptions that this makes. By default, it assumes that the sun is by default, the default setting of the sun is directly north at a 45-degree angle from the center of the digital elevation model. The digital elevation model is assumed to be a flat plane, like I mentioned, with the sun infinitely far away and light beams parallel. Azimuth values in the function definition are assumed to be modulo 360, so north is 0, east is 90 degrees, south is 180 degrees, and west is 270 degrees. And the altitude angle values are expected to be between 0 and 90 degrees. And so with this function that I've defined above, I can just say, give me a shaded relief image of the geoelevation data with the azimuth at 0 degrees and the altitude angle at 45 degrees. And here is the resulting image that we get. We can also make this interactive. So for instance, maybe I have a manipulate here, and I want to play around with the azimuth or the altitude angle, for instance. And because Wolfram Language has many other tools built in for computing the positions of the sun or various astronomical bodies, we can use something like sun position over Crater Lake with a particular date range to get a time series of sun positions and use list animate with this shaded relief image function that we defined earlier to represent the change in illumination over this area as the sun moves around in that particular time series. So here's what that might look like. And I apologize for the scaling issue here. We could also apply the shading result as a texture to a 3D representation of the digital elevation model. So here's an example in which, again, we have the Crater Lake representation, but we have a digital elevation model represented in 3D. And because it's in a manipulate, I can still go around and change these particular values, and it will update. In this case, for some reason, it's just taking a little while. It will update, and you can sort of get a more intuitive sense maybe than if you were just looking at the raster of what's going on. All right, I have about 14 minutes left, which is good because I think that's just about what I need. Here's the last example I want to cover today, which is slightly more out there example. Essentially, so the idea is, can we break up a satellite image into patches and see how fractal, how rough or self-similar those patches are at different scales? So there's I have two functions that I've implemented for this. One to compute the one-dimensional power spectrum of an image, and another to then take that image and compute a value that captures the self-similarity of that image. I'm going to skip over the implementations here just because they are a little bit more complicated and possibly not worth really digging into with only 14 minutes to spare. So the big picture here is that the degree to which the slope of a one-dimensional power spectrum of an image matches -2 is a fairly good estimate of how self-similar or fractal the image is. And so with this, we can make a tool that allows us to capture the fractalness of images. So here, for instance, I've applied this image self-similarity function that I've defined in this section here to an image of a Barnsley fern, and we get this result, which is a small negative value close to 0. The way the function works is that the closer the value is to 0, the more self-similar the image is considered to be. So we can apply this now to sort of to get a sense of the local landscape self-similarity of a geographic of an image of a landscape, of a satellite image of a landscape. So here I'm fetching some satellite imagery for Bar Harbor in Maine. So I have this nice satellite imagery which I've assigned to this variable. I then partition that image, for instance, into so I asked here for 1 mile radius. So these are going to be half a mile squared partitions, cells, I suppose. And then I can apply, using map, the image self-similarity function to every one of these cells, and then represent the result using array plot. So here's self-similarity of half kilometers squared patches, landscape patches over Bar Harbor. And this extends fairly easily. If you want to then represent it, you could then compose these. You could partition the image at different scales and make a sort of pyramid of self-similarity. So here's a first step towards this, in which you start with the geo image. This is the number of partitions for a given side that we want to take in subsequent steps, and then I can simply use table to partition the images into 4 and then 8 and then 16 and then 32, and map the image self-similarity function over all of these cells to construct these other self-similarity local self-similarity arrays. So here's the first one we computed. Here's the one here's the ones where we subdivide one extra step, and then we subdivide an extra step further, and then we subdivide one step further. And you can see for all of these, this is the same scaling applies, where the closer you get to 0, so the closer, the more light these pixels are, the more rough or the more self-similar the image is considered. You should keep in mind also that a confounding factor here is the resolution of the image. So if you have a very low resolution geo image, the self-similarity that you'll get for I don't know, 10 by 10 pixel image is going to be a lot less meaningful than the self-similarity measure you'll get for 1,000 by 1,000 pixel image. But this is just a general way that you might start to think about the local self-similarity of geographic landscapes. And you can also do another approach that you might have here is you might decide to apply this function using some kind of convolution. and then you can think a little bit about, what kind of kernel you might use. So you might have some Gaussian kernel that goes over a geographic image and computes the local self-similarity in a more continuous approximation. But I haven't implemented that to demonstrate for you today. Right. I want to leave you with just one last recommendation, which is just resources for learning about GIS in the Wolfram language. There are plenty of great resources for learning about geographic computation in Wolfram language. There are sources inside the Wolfram language documentation on the Wolfram website. For instance, the core areas page in geography has a great gives you a great starting point from which to branch out into different areas of geographic computation in Wolfram language. If you want a more gentle GIS introduction, there is this page on the Wolfram Learning Center for geography and GIS. And then there are plenty of guide pages inside the Wolfram language documentation. For general reference, you can also consult the documentation, and then there are also general, for people getting into Wolfram language, I also want to recommend these general introductions to the Wolfram language on Wolfram U. So having gone through all of this, I guess I can answer some questions if we have any questions from the audience. So we have a question from Carrie. Does Wolfram language have data on food deserts built in? I don't believe so, though we do have data about foods. I don't think we have data about the availability of foods and connected to particular geographic regions. Not presently, but it's a great idea, and it's the sort of thing that probably would make an excellent addition. Charles asks if this notebook is posted and where he can get it. I haven't posted this notebook yet. I'm going to make sure that it's available for download attached to the page for this particular talk after I wrap up. Ian asks, with the Mapbox satellite images, is there any way to get the date and time when the image was captured? And are historical images available as per Google Earth? I'm not that I'm aware of, but this is something that maybe is worth digging into a little bit further. Arnaud asks mentions not a question but a request. Would be really nice to have a data repository entry that has all these base map URLs, so the end user doesn't have to figure these out. I agree, and this is something that has been a bit of a side project of mine for a little while. I've been gathering a bunch of different base map XYZ GeoServer endpoints. This is something maybe we can talk about another time. All right. Well, we have 5 minutes to go. If there are any other questions, please feel free to ask them in the Q&A section, and I'll be here for the next 5 minutes, just looking out in case any of them come up. If not, then we'll sort of gently wrap up as things go. I suppose since we have a little bit of extra time, maybe I can go a little bit more into the implementation for the one-dimensional power spectrum of an image. So the way that this works is by first, wait a minute. Okay, the way that this works is first we compute an image that sort of represents the distance of any given pixel to the center of the image, given particular image dimensions, and then we use that image we fetch, essentially we bin together from a starting image the pixels at equal distances around the center, using this image on the periodogram, the image periodogram corresponding to that image, and then from these binned values we can reconstruct the one-dimensional power spectrum of an image. So here, for instance, I can use this image 1D power spectrum data with a Barnsley fern image and represent for the individual channels of the image what the power spectrum looks like. And then I can do this for different images. And then the image self-similarity essentially is just looking at the slope of this this line in this log plot, and seeing to what extent it matches -2, and then returning the distance from -2 that we get when we get when we fit using least squares aligned to these slopes. So this is the insight behind how this image self-similarity function works. And I'll make sure that this notebook is available for download. So given that there aren't any new questions coming in, I am going to wrap up here. Thank you very much to all who joined. And if you have any other follow-up questions about GIS and the Wolfram language, feel free to contact me. Feel free to reach out to me any way that you'd like. And I appreciate you all for coming. Thank you very much.